Hi there. So in this section, we continue our discussion on probability. So if you recall, in the last section, we were looking at tree diagrams and their counting principle, and I sort of went ahead and gave you a soft launch into probability. And so we'll just look at probability in a little bit more of a detailed format here in this particular section, okay? So we'll start this section with some definitions right out of the gate. So the first one is an experiment, and that's any controlled operation that can give us a set of results. So things that we'll be looking at would be tossing a coin, rolling a die, selecting from a deck of cards, okay? Possible outcomes then, if you roll a standard die, then you know you can get the numbers 1 through 6. You flip a coin, you can get heads or tails, and so on. Events are any sub-collections of those experiments. So let's say you're tossing that coin and you have an event where you've got 2 heads face up, okay? Or 1 heads and 1 tails. Our sample space is the total set of possible outcomes for an experiment. So when we roll a die, we know that we can get the numbers 1 through 6. When we toss a coin, we can get heads or tails, for example. Equally likely outcomes are outcomes where the probability is the exact same likelihood of occurring. So whenever we toss a coin, heads or tails, right? Heads 1 out of 2 times, tails 1 out of 2 times. All right, so let's talk about probability of event. Our formal definition for probability of an event is equal to the total number of ways that the event can occur divided by the total number of outcomes in your sample space. So that's why it's going to be really important that we're aware of our sample space as we work through our problems, okay? So let's come down, let's do a couple of these together. So in example 1, I say, well, what's the probability to roll an odd number with a standard die? So think about what your sample space looks like, right? When you roll a standard die, you can get these numbers, 1, 2, 3, 4, 5, and 6. Now, I want the probability of getting an odd number, so I ask myself, well, how many numbers on this die then are odd? So remember, odd numbers, 1, 3, and 5. So there's 3 odd numbers out of my total 6 numbers. Reduce that, divide them both by 3, and we get 1/2. All right, let's do one more, and then I'll talk to you about your calculator. Down below in example 2, it wants to know what's the probability to roll a number less than or equal to 5. So again, our sample space, 1 through 6, 1, 2, 3, 4, 5, 6, when we roll a die. I want to know this time, what's the probability that I get a number less than or equal to 5? So if I'm looking at my sample space in here, all of these numbers that I'm underlining, those are all numbers that are less than or equal to 5. So that's how many numbers? 5 out of 6. That cannot be reduced. So that 5 out of 6 is my final answer. Come back up here. That 1 out of 2 is my final answer. All right, so let's talk about for our answers for all probability. All probability in this unit will be listed as fractions in reduced format. So in terms of how do you enter this in your calculator, if you have the large like TI 83, 84 calculator, then all that needs to happen for you is you can just type in, it's nothing fancy, you just type in 3 divided by 6, hit enter, you're going to get a decimal, you get 0.5, and then if you hit math, enter in your calculator, it will change that 3/6 into a reduced fraction, which will give you then 1/2, okay? If you have the other calculator that I recommended, if you have a smaller calculator, the one that I recommended on your syllabus was the TI-30X2S. It uses these 2 functions. So you would still type in 3 divided by 6, hit enter, it's going to give you 0.5. You're going to hit then second, which is that blue key on the top left, PRB. So then you're going to hit PRB, second PRB. And I believe, I don't have that calculator right here in front of me, but I believe that is 1 over to the right and 1 under, if I'm remembering correctly. It's really close to that second key, okay? But you hit second PRB and then hit enter, and it will also change you back to a fraction, okay? A reduced fraction. It will reduce your fraction for you. So, some fractions are easy to reduce, and you may be able to do them in your head, but some are a little more, little higher numbers, and so using those calculator features is definitely worth your while, okay? All right, so now let's come on down below and let's talk about if we wanted to choose more than one item in our probability. And so in these particular cases, we're going to be concerning ourselves with whether or not we're looking at with or without replacement. And so we'll calculate those probabilities with or without replacement, depending on how it's indicated. And then what will happen is we'll multiply those probabilities together to get our final answer. So you'll see that play out here in the second part of example 3. I started us here with, suppose you have a jar containing 3 red marbles and 5 green marbles. I want to find these couple probabilities down here below. I'm just choosing one marble at random for my jar. So if I'm just choosing one marble at random for my jar, I want the probability that it's red. So I ask myself, well, how many marbles are red in the jar? That'd be 3. Out of how many total marbles in the jar? So add your red ones and your green ones together. 8 total marbles. That cannot be reduced. That's my final answer. All right. Scoot over here to part B. Find the probability that whenever you choose your one marble from your jar, that's green. So how many green marbles are there? 5. Out of how many total marbles in the jar? 8. And again, that cannot be reduced. So that's our final answer. All right, so now let's come on down below. Let's say, for example, we wanted to choose 2 marbles from our jar, okay? So, like, again, we're going to be focused on whether or not it's with or without replacement, like we talked about in the last section with our tree diagrams. And then from there, once we find our probabilities for our 2 marbles, we'll multiply them together, and that'll give us our final answer, okay? So in part A, it says without replacement. So that means then, remember, without replacement, that means I choose my marble, I don't put it back, I hold on to it, and so then when I go to choose my second marble, I've got less in the jar to choose from, right? So think of this as, well, here's choosing marble 1, and there's choosing marble 2. So when I go to choose marble 1, how many marbles, and I want the probability that both of them are going to be red. So when I go to choose marble 1, how many red marbles are in my jar? Simply agree, there's all 3 of them there, out of 8. Now, since this is without replacement, I'm holding on to that marble. And you also go into the assumption that you chose a red marble, okay? So now when you go to choose your second marble, how many marbles are left that are going to be red? That'd be 2 left, out of 7 now, right? Because you've chosen that first marble, it's out of play. So we started with 3 red marbles out of 8 total marbles in our jar, right? We held on to our marble, we held on to that marble, so then when we went to, and we assumed that what we chose was a red one. So now when we go to choose our second marble, we'll only have 2 left that could be red out of the 7 total in the jar. We multiply straight across, get 6 over 56. That can be reduced. Again, so you're starting to get a little bit bigger here. Use your calculator button, your math, enter, or second PRB. You type the fraction in first, 6 divided by 56, hit enter, get your decimal, then do your math, enter, or second PRB. Or if you have a different calculator and you don't know what your button is, take a picture of it, send it to me via email, and I can, most of the time, I can talk you through your couple of keystrokes that you need to do, okay? Here I can divide them both by 2 though, and I should get 3 over 28 as my final answer. Okay, let's scoot over to letter B. This time it's with replacement. So that means I'm going to choose my marble, I'm going to look at it, but then I'm going to put it back. Okay, I still want, now I'm choosing my 2 marbles. So here's my first marble, there's my second marble. I want the probability that both of them are going to be red. So we know when we choose that first marble, there's 3 red ones in our jar out of our 8 total. Like I said, we picked it out, we looked at it, now we put it back. When we go to choose our second marble, how many are red? That one's still back in there, right? So you still have 3 to choose from out of your 8 total. Multiply straight across, we get 9 over 64. That one actually cannot be reduced, but if you ever, whenever you start, like I said, getting larger numbers like this, you might question whether it can be reduced or not. You will lose points if you don't reduce all the way. Just pop that in your calculator, use your math, enter, or your second PRB, change it back to a fraction. If the fraction can be reduced, your calculator will do it. If it can't be reduced, then your calculator will just give you that fraction right back out at you, okay? So there's no harm, no foul in that, okay? All right, let's flip it on over. I've already been sort of alluding to this, but there are multiple ways that you can express a probability. It can be a fraction in lowest terms, which is what I'm going to prefer and require that you answer for me. It can be a decimal and it can be a percentage. But if you think about it, not everything is perfect. And so in many cases, those decimal and percentages have required that you do some kind of rounding. And so once you start rounding, your answer is not quite as accurate as that fraction is. Okay, so I'm always going to ask that we put all of our answers to probabilities as a fraction in lowest terms. And so like I reiterate it down here as well. To remain as accurate as possible, all of your probabilities should be written as fractions in lowest terms so that you don't lose points. Okay. All right, so let's move down to a couple of extreme cases. So the first one is an impossible event. So the impossible event means the event can't happen. So its probability has to be equal to 0. So I looked at here, the example that I gave you was rolling a 7 on a standard die. So think about your sample space when you have a standard die. You can get the numbers 1 through 6. What's the probability of getting a 7? There aren't any 7s on that die. You can never happen. Out of 6 total possibilities, 0 divided by anything is 0. Final answer. Can never happen. Okay? Compare that to the probability of a certain event. That means the event has to happen. Its probability is always 1. I'm also rolling a die here, so I'm going to put out my sample space 1 through 6. Here I'm asking you, what's the probability that you roll a number greater than 0? And so if you think about it, every single one of these numbers is greater than 0, so that'd be 6 out of 6, which reduces to 1. All probabilities are between 0 and 1. Okay, they can never be bigger than 1. They can't be negative. So all probabilities are between 0 and 1. All right, so let's come on down below and let's talk about our 3 different types of probabilities. And just so you know from the get-go, we will only be focusing on the top 2. We really technically can't focus on the bottom one. The first one is a theoretical probability, and so that's based off of known information. Based off of known information. So what I mean by that is like we've been talking about, when we roll a die, it's a standard die, everybody knows that it has the numbers 1 through 6 on it. When we toss a coin, everybody knows then it has a heads or tails. And the other one that we'll be looking at quite a bit that is known information is picking from a standard deck of cards. And we'll touch base on that here in a few minutes. So a theoretical probability, like I said, is based off of information that is widely known, everybody knows to be true. Empirical probability, though, on the other hand, is where an experiment has been conducted. The information in regards to that experiment is being relayed to you, and then you're asked to make a probability prediction from the information provided. So here's what I mean. So here an example, I say that Harry puts up a bird feeder in his backyard, and he starts to notice the type of birds that come up to the feeder. He's spotting 5 finches, 3 blue jays, 4 cardinals, and 6 mockingbirds. Okay, so he's put this feeder up. He's told us now the types of birds and how many of each one he's spotted. Now, what he wants us to do, what we're asking you to do now is, what's the probability that the next bird that comes up to the feeder will be a blue jay? So we base our probability off of what's already been seen. So how many blue jays have come up to his feeder? We agree that'd be 3 out of the total number of birds that have come up to his feeder. So we just count over. So we got 6 and 4 is 10, plus 3 will give me 13, plus 5 more. Is that 18? I can reduce that, divide them both by 3, so 1/6. Final answer. Okay. It's a real subtle difference. Okay, and you'll know. You mean am I going to ask you, is this theoretical or empirical probability? No, I'm just going to ask you to find the probabilities. Okay, and so you're going to know, oh, well, if she's asking me from a standard die, I'm supposed to know what's on a standard die. That's the numbers 1 through 6. But if it's empirical, I have to give you this kind of information. The last type of probability, like I said, we will not cover in this class, but is known as subjective probability. The example that I gave you here was rain probability, but probably even a better example for this area in southeastern North Carolina is hurricane probability. You know when it's hurricane season and we have one out in the Atlantic and it starts to become all the talk on by the meteorologist on the nightly news, especially when it starts getting really close. They start showing you the spaghetti models. Those spaghetti models is the idea of subjective probability. It's based off of models and experience and intuition from what they believe to happen, okay, or believe may occur. So for that reason, we would not be able to calculate that type of probability, okay. All right, so let's scoot on down here to example 4. In example 4, we're going to be looking at some probabilities that we're going to be, again, going off of known information. We're going to be drawing one card from a standard deck of cards, and we want to find these probabilities. What I'm going to do is I'm going to do the left-hand side here with you and let you pause the video, try the right-hand side, and check yourself by the solution key. So over here on the left-hand side, and actually let me remind you that on the back side of your formula sheet, there is a standard deck of playing cards. There are 52 cards in a deck. And I have it arranged there on that sheet of ace through 10, and then you have jack, queen, and king. Ace is considered a low number 1 card. So ace is like a low number 1 card through 10. So ace through 10 are your number cards. Jack, queen, and king are referred to as your face cards. you have 4 suits. You've got your hearts and your diamonds, which are red, and then you have your clubs and your spades, which are black. Each one of those suits has 13 cards in it, and I think I hit everything. Okay, as far as, just sort of giving you a lay of the land if you've never played with cards or, worked with them in any way. Okay. All right, so let's come on down. Like I said, we'll do this left-hand column here together. So remember, in our last section we talked about ands and ors. So we'll start here and straight out the gate here in part A with an or statement. I want the probability of getting a 7 or a 9. So remember, when we use that word or, we can have one or the other or both. We just can't double count, okay? So we ask ourselves, looking at our standard deck of cards, how many 7s are in your deck? Hopefully you agree, there's 4 of them. Plus, how many 9s are in your deck? Also, 4 of those. There's no overlap, so I get to count both of them. Add them together, we got 8 out of 52. That can be reduced. I can divide them both by 4. 2/13, final answer. All right, so then we'll move on down to letter C here. I want the probability of getting a diamond. So I ask myself, okay, well, how many diamonds are in my deck? Hopefully you agree. There's 13 of them out of total number of cards, 52. That can be reduced. I can divide them both by 13. 1/4, final answer. Okay. All right, let's go on down here to letter E. I'm using that word and, so remember for and, you have to satisfy both conditions. If it only has one condition, it can't be counted. You can only count those that are both, in this case, going to be a jack and a heart. So you look over your set of playing cards there. How many cards are both a jack and a heart? So you've got to be both of those pieces, a jack and a heart. Hopefully you agree. There's only one card in that deck. It's both a jack and a heart. It's a jack of hearts, right? 1 out of 52. And of course, that can't be reduced. All right, letter G. I want the probability of getting a face card or a spade. Okay, so I count over first. Okay, how many face cards are there? So remember your face cards. Those are your jack, queen, and kings. Hopefully you agree. There's 12 of those. Plus, now when I go to count my spades, there are a total of 13 spades, but I can't include the jack, queen, and king, right? Because I've already included those in my face cards. So I'm really just going to be counting my number cards over here for my spades. I'd only have 10 cards left to choose, right? Add that together, we get 22 out of 52. That can be reduced, divide them both by 2. 11 out of 26, final answer, okay? Definitely pause that video, try that right-hand column on your own, check yourself by the solution key. I'm going to flip it on over. All right, I'm going to come over here to the next example. And I'm still looking at a standard deck of cards, but this time I'm going to draw 2 cards. So if I'm drawing 2 cards, I want the probability of drawing 2 hearts from a standard deck of cards, and we're looking at with replacement and without replacement, okay? So here in letter A, if I'm with replacement, so remember I'm going to draw myself 2 blanks here because I'm drawing 2 cards. If I were drawing a third card, I would do another blank for that third one, and then I'd multiply straight across. But here it was just drawing 2 cards, so 2 blanks. All right, so we know we've got a total of 52 cards, and this is with replacement. So when I go to choose my first card, I ask myself, how many cards in my deck are hearts? You agree, there's 13 of them. It's with replacement, so I'm going to pick my card, I'm going to look at it, and I'm going to put it back. So then when I go to choose my second card, I still have all 52 cards to choose from, and how many of them are hearts? Still 13. I multiply straight across. I got 169 over 2704. That can be reduced. I can divide both of those, the 169 and the 2704, both by 169, and that would give me 1 over 16. Final answer. All right, so then I'm going to scoot over here to letter B, this time without replacement. I'm still trying to draw 2 cards from my deck, so I'm going to draw myself my 2 blanks. When I go to choose that first card, we still know that there's 52 cards to choose from. How many of them are hearts? There's 13. But this time, since it's without replacement, when I choose my card, I'm holding on to it, okay? And again, we make the assumption that that card that we chose was a heart. So when I go to choose my second card, how many hearts do I have left? 12 left. And also, since I've held on to that card, how many cards are we choosing from? Hopefully you agree, that'd be 51. So now when I go to multiply straight across, I have 13 times 12, which will give me 156. And then on the bottom, 52 times 51 will get me 2652. Reduce, and you should land at 1/17. Final answer. Okay. I'm going to let you pause the video and try example 6 on your own. And then let's come on down to example 7 together. In example 7, it's really, you're still finding probabilities. I just have given it to you in a different format, a table format. So maybe let's look at A and B here together for this one and let you try C. Excuse me. So here we're looking at car and SUVs made by GM and Toyota. So we can see their car preferences, SUV preferences, and total number of people that were surveyed here. So 130 total people. So let's say we have one person's chosen at random. Find the probability that he or she would have selected a SUV. So we follow, here's my SUV row, follow it over. So total number of people that chose an SUV, that'd be 45. Out of total number of people that were surveyed, 130. So 45 out of 130. That can be reduced. Hopefully you can divide them both by 5. So that'll get me 9/26. Final answer. All right, we'll do one more here together. Find the probability that person selected a Toyota. So here's your Toyota column. Follow it all the way down. Total number of people that selected a Toyota, 47. Out of total number of people, 130. That cannot be reduced, but again, like I said before, if you don't know, pop it in your calculator. Use your fraction button. Again, if it can reduce, it will. If it can't, it's just going to give you that fraction right back. Okay? I'll let you pause and try example C on your own. All right, and let's come on down here to example 8. All right. In example 8, we're throwing back to our tree diagram and sample space. Okay, so here it says that Barry has 3 shirts in his closet, a red, white, and blue one, 2 ties, black and gray. And we want to say that suppose he chooses 1 shirt and 1 tie at random. Okay, we want us to draw a tree diagram and list out our sample space. So I'm going to draw my 2 blanks representing choosing the shirt and choosing the tie. So when he chooses his shirt, he has how many shirts to choose from? Hopefully you agree. That'd be 3 choices, right? The red, white, or blue. Then when he goes to choose his tie, he's got how many to choose from? It'd be 2, right? The black or gray. Multiply straight across, we get 6. So remember, this counting principle tells us how to construct our tree diagram. It says start in the beginning and branch off 3 times. And at the end of that branch, put in your shirt choices, right? So your shirt choices were red, white, and blue. Then move over to your ties, and then that number tells me to branch off twice from each one of those. And then put in my tie choices, and they can be black and gray. So I'm going to put BL for black and gray. Now remember, you should end up with 6 total ending branches. So 1, 2, 3, 4, 5, 6. Remember, you read these tree diagrams from left to right, top to bottom. So now my 6 points in my sample space. I could have a red shirt, black tie, red shirt, gray tie, white shirt, black tie, white shirt, gray tie, blue shirt, black tie, blue shirt, gray tie. Okay, so those are my 6 total possibilities. All right, if you want to pause the video and try these probabilities down here below by yourself, go for it. I'm going to go ahead and do them though, and talk you through it, and then let you try example 9 solo. Okay, so in letter B here, it wants the probability that you get a red shirt and a black tie. So remember that word and, you've got to satisfy both conditions. If you only have one, you don't get to count it. It's got to have both a red shirt and a black tie. So that only happens one time, right? That's the only, that very first one, red shirt, black tie, that's the only time that happens. So 1 out of 6. All right. Next one, white shirt or a black tie. So remember, or, you can have one or the other or both, just don't double count. Okay, so I can include both of these because they have white shirts, and I can include this one because it has a black tie, and that one because it has a black tie. So there's 3, 4 out of 6 possibilities there. That can be reduced. 2/3. And then lastly, I want the probability of getting a white shirt. We just count over here. I've got 1, 2 times. So that means the tie color does not matter. So that happens 2 out of 6, which can be reduced to 1/3. Okay. All right, I'm going to let you try example 9 on your own and check yourself by the solution key. All right, thanks a lot. Bye.